Limit of a polynomial function. Basically, if a polynomial function, then you can plug x in the, as x approaches c of p of x, you can just plug in the c. You can do that anywhere for any function that's continuous. Because if a function is continuous, we know that from the left and the right it approaches the same thing. Also at the value it's the same thing. So from the left and the right, if it approaches the same thing, then the limit will always be that, right? So anywhere a function is continuous, even if it's not a continuous function. So for example, a rational function may look like this and like that, right? From here to here, if I ask you for any limits, you can just plug it in. From here to here, if I ask you any limits, you can just plug it in. The only place you can't just plug it in is on the vertical asymptote, right? So wherever graphs are continuous, even if it's not a continuous function, which that is not, it has an asymptote, it has a break, you can always just plug in the value, which we've been doing for most of these, right? So this one here, this is a quadratic. So if it's a quadratic, we can just plug in the value because it's continuous at 3. It's continuous actually everywhere. So when it's continuous, from the left and the right, the limit will exist, but also at that coordinate it'll be the same value. So we can just find like f of 3, technically. So we're going to go 4 times 3 squared minus 3 plus 2. And we get 36 minus 3, which is 33, plus 2, 35. Don't all answer at once. Thanks, Joe. Gotcha. Okay. So we plug in -1. We get 7 times -1 to the 5 plus 4. This is a quintic function, so we can plug it in. There's 2 times -1 squared. And so we're going to get -1 to the 5 is -7. -1 cubed is -4. -1 squared is positive minus 2. So we get -13. And then the last one is a degree 6 function, so we can just plug it in. How we know it's a polynomial? Remember, polynomials have exponents that are whole numbers, right? So you can have x to the 0, because this one technically has x to the 0. That's why I could say whole numbers, right? Because x to the 0 is just 1. So your constant actually has a variable of x to the 0. So polynomials always have exponents that are whole numbers. Hola, señorita. Okay, so this one, we're going to fill in a 0, and we're going to get 10, 0 to 6, minus 4, 0 to the 5, minus 8 times 0, plus 5 is 5. Okay, so we literally just found the y-intercept, correct? When we're finding the limit at 0, we are actually finding the value at that when we're just plugging it in and have never not doctored the equation. So yes, f of 0 would also be 5, but the limit is not what the value is. The limit's what it's approaching. We agree? Okay. 10. This will be a homework question. We're not doing it at this very moment. Okay, example 10. The limit as x approaches 1. So what we always want to do first is plug that value in and see if it gets us a problem. If it gets us a problem, we're going to have to do something algebraically to get rid of the problem. If it doesn't give us a problem, good, cool. It's probably a place where it actually is continuous. So this graph is a rational graph. We agree? It's a rational graph. We learned about rational graphs with 3x1, every single one of us. Rational graphs often have asymptotes. Sometimes they do not if you have an addition of squares in the denominator. But I told you, if I ask you for the limit where that graph is actually continuous, even though it isn't a continuous function, you can just plug it in, right? It's not going to result in a problem. So whenever you're given an equation, the very first thing you should do is try and plug that value in and see if it gives you a problem. If it doesn't, plug the value in. It's just a continuous part of the graph. So if I plug 1 in, I'm going to get 9 in the denominator. Is that a problem? No. So let's just plug it in. So that's a continuous place on this rational graph, right? So the moment we plug in the 1, table people, the moment we plug in a 1, I blame Jack. The moment we plug in a 1, the limit drops off. So we don't, well, I'm plugging the 1 in, so the limit's going to go away. I'm going to get 3 times 1 cubed minus 2 times 1 plus 1 over 4 times 1 squared plus 5 And so I'm going to get 2 over 9. If I look at B, B is a radical graph which has a restriction, embedded in a rational graph which has a restriction. I know x can't equal 1, correct? Because if it equals 1, I have a problem. There's also a value for x that can't happen, and it would make negative under your square root. Normally, this one has nothing, because no matter what I plug into x, it's going to become positive. Positive times 3 is a positive, plus 1 is still positive. So I'm not going to get a negative under there either, so there's no restriction. So my only problem child with this is x equals 1. They're asking me for x equals 4. So I can just plug it in, right? I can do direct substitution. So I'm going to get 4 squared plus 1 over 4 minus 1. So I get square root of 49 over 3, which is 7 over 3. And we'll have this one. Okay. This is where it gets harder. So everyone has to pay attention. So those ones we could just plug in because I asked you for an x value that wasn't the problem, right? That wouldn't make that denominator 0 or wouldn't make the radical negative. But now we got problems. If I plug negative 2 in, I direct substitute it in, I'm going to get negative 2 squared minus 4. 4 minus 4 is 0. Correct? That's a problem. So what I want to do, and we talked about this before, is we want to get rid of the problem child. So we want to get rid of the factor that will make that denominator be 0. So let's factor the top and the bottom first. So we're going to get the limit as x approaches negative 2. The top we factor what multiplies to give me 6 and adds to give me 5. X plus 2, x plus 3. And the bottom's a difference of squares, so I get x plus 2, x minus 2. You see it? Okay, everyone put your pencils down. Most of you guys will just do this algebraically, but not really comprehend why we're doing what we're doing and why there's a problem. What of these two factors in the denominator, which one of those is actually the problem? The x plus 2 one. Why? When I plug in that negative 2, that actual bracket will turn to a 0. 0 times anything is 0, making the denominator 0. That's my problem. So I know this is the one that is the issue. If I plug negative 2 into here, I get negative 2 minus 2, I get negative 4. That's fine. I can have a negative 4. My denominator just can't have a 0, right? So that's my problem child. So whatever is the problem child, that's the one I need to get rid of. So you need to know that somehow I need to get that binomial in the numerator so that they can cross off, problem child's gone, then I can direct substitute, correct? So the moment you have two factors in the numerator and denominator that are the same and they cancel off, in 30-1 we call that a point of discontinuity, correct? In calculus we will call it a removable discontinuity, yes? So that means that from the left and the right, they're still approaching the same thing. When it's a removable discontinuity, that means there's an open dot. There is no value there, right? There's no y value there. If I asked you for f of negative 2, you would tell me it doesn't exist because there's an open dot. We agree? But from the left and the right, it's going to approach the same thing if it's just an open dot because they're coming to the same value, yes? So the limit will exist on a removable discontinuity, but f of negative 2 will not, right? If I direct substitute it in there, I'm going to get a 0 in my denominator, so it doesn't exist. So we know that this is a removable discontinuity, and we know that the limit exists because whenever we have a removable discontinuity, we have a graph that's like coming in and out from the left and the right, same spot. This value just doesn't exist. We agree? Okay, so those cancel off. My problem child's gone. I can now fill it in. I get negative 2 plus 3. You can pick your pencils back up if you have them still down. Negative 2 minus 2, and I get 1 over negative 4. So not only is this the limit, so I can write this, limit as x approaches negative 2 of this function is negative 1/4. So on the left and the right of the point of discontinuity, it's getting closer and closer to negative 1/4. Why is that? Because I just found the y of the point of discontinuity, or the removable discontinuity is what we're calling it now. Okay? Okay. B. I'm not going to tell you how to do it. We're going to talk about it. See if you guys can come up with a way to help me out. So x minus 5 is my problem child. We agree? We see it there? If I plug the 5 in, I'm going to get a 0 in my denominator, yes? So that is the problem. That means somehow I need to get an x minus 5 in my numerator somehow so that those bad boys can cancel off. Problem child gone, I can plug in. Right? That's ultimately what we're trying to do here. So, I'm not telling you how. You guys are going to help me. I need 2 square roots to turn into something without square roots. Grade 11 and a bit of grade 12. What did we do? What did we do to get square roots to go away to be not square roots? Because I need an x minus 5 without square roots. Okay? Nope. That would be if we had one individual one. That is true. That's what we're solving. Absolutely. Any other idea? I had to give hints. Nope. What did you say, Folger? That conjugate! Boom, shaka, freaking laka. Ooh, I recorded that. Yeah. It happened. Okay. Okay. So square root x minus square root 5. If we multiply by the conjugate, the reason why you multiply by a conjugate is the square roots go away. That's the point of it, right? It's called rationalizing the denominator is what you did in grade 11. You rationalized the denominator, you made it be something that wasn't radical anymore, right? But we don't just rationalize denominators here. We sometimes rationalize to rationalize. We want to rationalize it. We want it to go from a root to a rational, right? So we're going to multiply by the conjugate. So here, we're going to multiply by square root x plus square root 5. So it's the exact same opposite terms. Now, guys, I told you I don't love memorizing. I love understanding. That makes math a heck of a lot better. So, pencils down. We all understand the conjugate's going to make the radicals go away. If you don't, in 2 seconds, you'll see they go away, and you'll be like, ah, yes. But my problem child is this x minus 5. We discussed this, yes? That's one that's causing me problems today. It needs to be crossed off in the numerator, yeah? Now, if I distribute this x minus 5 into the root x plus root 5, is that a good idea? No, because I want this x minus 5 to go away. If I embed it into here, it's now all squished with other things, and why do we want that? So what we need to know is, we need to know that the two that are not conjugates, we always just leave them as brackets. Now, a lot of people just memorize that. Don't memorize it, understand why. We want this x minus 5 to go away. The only way it can go away is if it's still an x minus 5, it matches x minus 5, and we cancel them off, right? So if you distribute them, you've now gotten rid of that x minus 5 nicely sitting there to cancel off. So we do not want to distribute the ones that are not conjugates, okay? So in my next step, I'm still going to write the limit as x approaches 5, because I haven't filled in the 5. I have not substituted in the 5. And until I substitute in, that limit's got to run along. The conjugates I will multiply. So I'm going to get root x times root x, which is x. Root x times root 5 is positive root 5x. Remember, when you multiply radicals, you multiply outside times outside, inside times inside. So coefficient times coefficient, radicand times radicand. And then we get negative root 5 times root x is negative root 5x. The reason why you multiply by conjugates, which is opposite terms, is because the two terms that have radicals are going to cancel off, because one's going to be positive and one's going to be negative, right? Reason why we do conjugates, opposite signs. And then negative root 5 times root 5 is negative 5, all over x minus 5 root x plus root 5. We do not put those together, remember? I'm going to show a separate step, but if you cancel it off from here, it'd be fine. But I'm going to show it so it looks better. The limit is x approaches 5. I still have not plugged in my 5, because I can't plug in my 5, because if I do, my denominator will turn to a 0 still, because the problem child's still here. In the top, I have x minus 5 in my numerator. In my denominator, I have x minus 5 and root x plus 5. Sorry, plus root 5. And now, remember when you have two terms with a plus or minus sign in between, they're sewn together, right? You cannot pull them apart. That's called a binomial, right? You can't like just cross an x off with an x and a 5 off with a random 5. X minus 5 is a full term. They're sewn together. Plus or minus signs sewn together. Multiplication signs are just kind of like lightly glued. So you can cross them off and pull apart, right? But when they're with a minus or a plus sign in between, they are sewn together. You cannot pull them apart. So x minus 5 is not being pulled apart, and the only way it can cancel is with a replica twin in the numerator. And currently we have one. Remember that when we cancel off, what's left behind? A 1. So you still have a 1 in your numerator, right? It doesn't just go away. So I get a lot of people telling me that it's root 5 plus root 5 and just give me the answer. But it's actually 1 over, right? This is still a 1 in my numerator. So I'm going to get 1 over. The moment my problem child is gone, I can substitute in, right? Now I won't get that 0. So I'm going to get root 5 plus root 5. What's root 5 plus root 5? It's the same as x plus x. 2 root 5. 2x, 2 root 5. So I'm going to get 1 over 2 root 5. Great thing about 31, you're done. No rationalizing denominators. Don't really care if we do. Okay? For C, guys, what's my problem child? The x or the x minus 3? The x minus 3. Why is the x minus 3 my problem? Yeah, because it'll give us 0. Paying attention, what if I did the limit as x approaches 0? What should be my problem child? X. So it depends on what limit I'm asking you to find. Right? You guys try C. Go. All right. So we're going to multiply by the conjugate. Same thing down here. We do not distribute the denominator because we need that x minus 3. Okay, now you go away. The x minus 3 to go away. So we write an equal sign. Check and make sure you have equal signs running down the left-hand side. It's important. These all equal each other. So this one equals the limit as x approaches 3. On the top, we're going to get square root x plus 1 times square root x plus 1 is x plus 1. Then plus 2 root x plus 1 minus 2 root x plus 1 minus 4. These cancel. And then I do not distribute the denominator. The reason why we do not distribute it is I need x minus 3 to cancel off. If I distribute it, I can't. So that's no good. So I'm left with x minus 3, square root x plus 1 plus 2. And then x plus 1 minus 4 is x minus 3, which is my problem child. Then my problem child cancels off. And once that's gone, the problem is gone, I can plug in the 3. The moment I substitute in the 3, the limit goes away. So I'm going to get 1 over 3 times 2 plus 2. So what do I get? 1 over? Yes, you're right. Then these questions will be due. Then we're flipping over to one more example, and then we'll let you work. Oh, so tough. Life is hard. So we're actually skipping example 12 right now. We're going to go to 13. We'll do 12 on Monday. Okay. Everyone, please. Shh. Example 13. If I plug the 2 in, I'm going to get a denominator issue, correct? So I'm still going to have to multiply by the conjugate. You're going to try that one out. And B, I have an x cubed. What am I going to have to do in order to factor that? Starts with S. Rhymes with synthetic division. Thank you. Wow, you guys are really on the ball today, Friday. Good job. Cool. Synthetic division. Yeah. So A and B, try it out. So this one, we multiply by root x plus 2 plus 2. Root x plus 2 plus 2. The top we leave the same because we are going to need to cancel off an x minus 2 in the bottom. We don't distribute the ones that aren't conjugates. The bottom we're going to get x plus 2. And then technically the middles will cancel off, and then minus 4. So we're going to get limit as x approaches 2, x minus 2, root x plus 2 over x minus 2. These cancel, and then I can plug in or substitute in 2 plus 2 plus 2, which is what? Okay. Some people are like, I don't know what to do. I'm not allowed my calculator for this one. Well, I know that I'm going to end up with an x plus 3 in the bottom. I know I'm going to need 2x plus 3's in the numerator to cancel off, correct? So if I go to do synthetic division, I can put x equals negative 3 here. Yeah, I didn't record any of this. Well, that happened. You're welcome, podcasting people.